All right, let's get started for today. Couple of announcements all about midterm 2, which is coming up next week, Monday evening. There are 4 rooms this time. They're not exactly the same set of rooms as last time, so check which room you are in. It's also on the midterm prep page. 4 different rooms based on last name. The topics are from lecture 12, which is probability, all the way through the perception lecture, which was last week Thursday. Inclusive last week Thursday's lecture. But those are the only topics. We're not going to ask you about the first 11 lectures, just 12 through 21. Of course, also corresponding homework, sections, and so forth. There's a midterm 2 prep page, which has past exams. Check those out. There are special midterm 2 office hours. Check out the schedule. There's a little Google Calendar thingy that you can just kind of use to import office hours into your own calendar. There's also a practice midterm. The idea here is that ideally you'd study for the midterm, you'd think you're prepared, you'd take the practice midterm. If you ace it, you know you're prepared, you're all good to go. If you don't ace it, still have some time left to prep some extra before the actual midterm. So the practice midterm is due on Saturday, right before midnight. Any questions about logistics? All right, let's get started with kernels and clustering then. So we're going to look at a different way of doing classification today. It's called case-based learning. Here's some motivation. Let's say you have non-separable data, as shown here. You might say, well, this green separating line is what I want, but you might also say, well, I know that these labels are not noisy. I know that the plus here really is a plus, and I want to be able to carve out a part of that region to label it as plus if I get new examples there. If you just use a linear classifier like the perceptron would give you, you wouldn't be able to do this. The best you can do is find the best linear classifier. It'll be something like what's shown here, and that's where it stops. Okay? At least as far as you've covered it in last lecture. So today we'll start looking at how to go beyond that and have more flexible decision boundaries. So what we can do is, instead of parameterize our decision boundary in terms of some hyperplane or some kind of function, what we could do is we could say, well, how about we classify based on similarity? So nearest neighbor classification proceeds as follows. Let's say you're supposed to classify any point in this region over here. There are 3 training examples. This is a plus, and this is a circle or negative. Okay. Now, if you're asked to classify any point in this box, for example, this point over here, what nearest neighbor would do, it would say, well, let's check which one of the 3 training examples is the closest to my new point. In this case, it'd be this one over here. You check the label of that particular one, it's plus, and so you'd classify this new point as plus. You can do this for every point in that region if you want, and then that way visualize where you'd have a plus label, where a negative. The plus label is where everything's white. The negative label or circle label is where it's green. And so you see here that you have a decision boundary that's shaped quite differently from what you're used to, because it's shaped based on the specific data points and wherever they happen to lie. You might say, well, it might be a little noisy to just go with the nearest neighbor because maybe the labels aren't always perfect. If that's the case, you could use k nearest neighbors. What you do there is you look at the k nearest points, and then you do a vote. You pick k to be odd for this to work out properly, so you pick some odd k, pick the k nearest points from your training set, and then based on those k points, you do a vote, and you find out which label has the majority vote, and that's what you go with. You can do this with multi-class classification too. It doesn't have to be just 2 classes. Essentially, you just need to have a number of neighbors such that there is no tie in terms of which class you'd end up with. If you only pick one neighbor, there'll never be a tie. Pick more than one, be careful you don't end up with a tie. The key issue here then becomes how to define similarity. So in this drawing here, we define it just as Euclidean distance in this plane. But you can imagine when you think about, let's say, emails and you want to see which is the closest email to another email you've seen, that maybe you need to do something a little more sophisticated, same for images and so forth. The trade-off here is that if you use a small k, you get the most relevant neighbors. So in some sense, it's best is the nearest points. But if the labels are noisy, then maybe you don't get enough information and might want to use a larger k to average out noise and have the signal prevail over noise. OK, so this is the first example of a totally different type of classification algorithm. What we've seen so far are called parametric algorithms. And what we're seeing today is a non-parametric approach. So this is today. This is last week. In parametric models, you assume some model. In naive Bayes, you assume a model of how the data gets generated. In Perceptron, you assume the model of what the decision boundary would look like. There are some free parameters in there. And based on the trained data, you find the best setting of those free parameters. The more data you have, the more accurately you can set those parameters. But at some point, as your amount of data gets larger and larger and larger, effectively what you get is convergence to some parameters. And those will be effectively the best parameters you can have. It won't go beyond that. In non-parametric models, what happens is, as you get more data, you can increase the complexity of your classification boundary. Right? So let's look at an example here. We have two training examples. So there's one here and one here. That's what the decision boundary looks like. Actually, with two examples, it looks like a line still. Now we have 10 examples. It looks like this, much more complex. 100 examples, you get even more complicated boundary. Now it turns out in this particular case, as you get even more examples, the boundary simplifies a bit again. You get this kind of crisp boundaries here that essentially have two regions, one here and one here for positive, and then the other part is the negative region. But what you see here happening is that the amount of training data affects the type of decision boundary you have. Initially it was a line, then it got more complicated, even more complicated, and then it got simpler again in this case. Whereas for a perceptron or a naive Bayes, the decision boundary will always be of the same type. It's just that the parameters will change with your data. All right. The ground truth in this case would look like this. So let's think about what we can do for a more realistic setting. Let's think about digit classification. So let's say you are given this digit over here, a scan of it. This is your training data. How do you proceed? You would compute which one is the closest match, or if you have a k nearest neighbor, you find the k closest matches, do a vote. Okay? So then the question is, what does it mean to be closest? Well, we encode these images by a vector of intensities. This is 256 numbers, one number for each pixel, a number between 0 and 1. Okay? So what similarity function could we use? Well, when we have vectors, there's one natural option, which is the inner product. You just say, well, similarity between two vectors is the inner product. So x dotted with x prime, x and x prime both in this case being 256 dimensional vectors. And this is, dot product is defined as the sum of the products of the corresponding entries. Okay. Often what's done for images is ahead of time normalizing the image, meaning that you make the norm of the vector representing the image equal to 1. What does this do? It makes it more invariant to lighting, or in this case, the scan darkness or brightness of whatever you collected. Then often, then the result will be that the lowest you can go, assuming all numbers are positive, is 0, when you have completely zero similarity, which means two orthogonal vectors. And the maximum you can get is 1. This is when the two vectors are completely identical. So by normalizing, everything gets put on a kind of common scale. It's easier to interpret what's happening. Okay, this might be a pretty naive similarity function, right? If a number is shifted over a little bit, the similarity between the vectors might be really, really low. So we'll have to start looking at better similarity functions to get this to work well in more complicated scenarios like this. So let's look into that. So actually, one thing I should highlight here is that when you run your nearest neighbor with similarity functions rather than distances, what you'll do is you'll look at which of your training examples has the highest similarity. rather than looking at which one has the smallest distance. All right? So what are some similarity functions we could look at? One we already saw is just inner product. You could do the inner product of the raw pixels that you got or the raw input you got. You could also compute a feature vector first, like you've done already for naive Bayes and the perceptron, and then inner product the feature vectors. Right. It's a very natural thing to do. Now you have flexibility in terms of choosing the features. You choose your features as the things that matter about these examples, and then this will be a meaningful measure. Simplified scenario is where the features are just the pixels and just f of x equals x. Doesn't have to be this particular form, but this is one form you could use. Now, if you want more invariance, you can start thinking about what you care about. Let's say you, in the case of digit classification, might care about invariance to rotation, scaling, translation, stroke thickness. So what you then want to do is you essentially want to say, well, this one here and this one here are quite similar because they're only rotated versions of each other. They still have the same meaning. There might be limits to it. A 6 is a rotated 9, so a 180-degree flip might not be as much as you might want to allow here, but you want some invariance to rotation, some invariance to translation and stroke thickness. So the question becomes, how do you incorporate this kind of idea into your similarity measure? So one thing you can do is you can redefine your similarity measure as S prime here, which is the max over all similarities of, and you maximize here over all possible rotated versions that you could pick. Effectively, you have some example, another example. You see how much you allow for, let's say, maybe 15 degrees of rotation. Within 15 degrees of rotation in each direction, you see how close you can get them. Whatever is the most similar you can get these two inputs to be, that's going to be your similarity metric, and now you're invariant to rotations up to 15 degrees. Okay? What this requires is this requires you to think about this all ahead of time. So ahead of time, you think about what are things I want to be invariant to. Redefine your similarity metric to have an internal computation that computes all these variants as you compute a similarity, and then pick the best one. There's something else you can do that effectively is the same thing, that sometimes is more convenient to work with, sometimes not, it depends, but you can also do training data augmentation. The idea there is that rather than, when you compute the similarity, looking at the max, which you did on the previous slide, do this all ahead of time. As you get your training data, you say, I'm going to rotate my training data in all possible ways. I'm going to translate it in all possible ways. I'm going to maybe skew it, maybe change the stroke thickness, and so forth. And now one digit that was labeled becomes maybe 1,000,000 digits with that label, which are the 1,000,000 variants you're able to come up with for that one training example. And so you're augmenting your training data, which can multiply it by a factor 1,000 or even 1,000,000 in many cases. And now you have a lot more training examples. Now when you measure similarity, you can just go through your training data, find the closest match. You don't need to do that additional computation anymore at test time. So you're doing it all ahead of time. So that's training data augmentation. It'll effectively result in the same thing. Any questions about similarity metrics and how you might want to augment things based on invariances you're aware of? Yes?
Could you explain the notation with R?
Okay, so what this notation means here, it's essentially saying if you have a vector that comes in, R is generating a curve in this 256-dimensional space, or it could be more than a curve if you allow for more than one variation to be induced, let's say translation and rotation. Then you'd generate a two-dimensional surface, and then you'd measure the distance between the two curves generated, or the two-dimensional surfaces generated from those two examples. That's one way to go about it. I mean, you can also just do it for one of them, then measure the distance from the one you keep fixed to the curve or to the surface you generated. Either way will be the same thing.
So using those input images, you're generating curves?
So you'd have this as your input image. this would result in, if you just rotate in this curve over here in a 256-dimensional space, which we didn't draw here, we just drew a 3-dimensional space on a 2-dimensional plane. But it would generate a curve, and that's your R right there. That's your R. This here is your, don't stick. That curve there is R applied to that thing. All right, so what we've seen so far is a new way of doing classification. Nearest neighbor-like approaches, what do? They compute some similarity function between examples based on the closest matches, maybe the single closest match or multiple closest matches, do a vote, based on that, decide on the label at test time. In contrast, what we've seen before when we looked at the perceptron, you explicitly at training time actually did something, right? With this nearest neighbor-like approach, you don't do anything at training time. Just store your data, you choose a similarity metric, and then when test data comes in, you use that similarity metric to help you decide what's closest. Perceptron-like approaches at training time do more than that. They cycle through the training data and optimize the parameters of your decision boundary to do as well as possible on your training data, while maybe tuning some hyperparameters on your holdout, based on your holdout data, to then hopefully do as well as possible on your test data, right? So it's a very different kind of approach. Here you have a real kind of training phase, and here